today we have Hugo Caselles-Dupré, and Hugo is a postdoc at the Institute Intelligent System and Robotics at Sorbonne University, and he's supervised by Olivier, Sigaud, and Mohamed Chetouani, and he's studying teachability and autonomous agent. He received his PhD in 2021 from the Flower Laboratory at ENSTA, Paris, ParisTech, and INRIA. And his research focuses on machine learning for artificial agents, and he studies how artificial agents in situated environment can learn and interact, and how they can perceive and learn from social partners. So the topic of today has been discussed during the last NeurIPS conference, and is pragmatically learning from pedagogical teaching signal environment. I give the floor to Hugo. Thanks a lot.
Thank you. So I will share my screen. So you can all see my screen now? Is that good?
Yeah, we can see your screen.
Okay, perfect. So thank you so much for the introduction. So today I will talk to you about our the research I'm conducting in my postdoc. So I'm actually going to talk about mainly one paper that we just recently presented at NeurIPS in New Orleans, and so this work is about getting some motivation from developmental psychology to improve on learning from demonstration methods. So the idea is that the way we demonstrate stuff as humans to kids, for instance, is a little bit far from what we actually do in reinforcement learning. So in reinforcement learning, we usually use optimal demonstration to do learning from demonstration. So for instance, this can be a demonstration from humans that perform the task optimally, or it can also come from other agents that use their policy to do the task optimally, depending on how they were trained. And what we actually see in cognitive science and developmental psychology is that human demonstration usually are not optimal. So for instance, rather than just doing a task, a human will try to show a task to a kid, for instance. So the idea is that instead of just doing the task, the human will exaggerate his movements to better convey what is the goal that he wants to achieve, and it will also select demonstration that disambiguate between the different goals that the teacher is trying to show to the kids. On the other side, also, we noticed that human learning involves pragmatism. So basically, the kids are really good at inferring what is the intent of other agents when they are doing stuff or demonstrating stuff. So they are really good at interpreting what the tutor or the teacher communicates, and thus they can deduce relevant information from that, compared to just observing a demonstration and not trying to really understand what the other agent is trying to do. So in this paper that I will present, what we do is that we try to implement pedagogical tutors and pragmatic learners using a Bayesian mechanism that is called Bayesian goal inference. And what we show in the paper actually is that combining a pedagogical teacher and a pragmatic learner, this results in faster learning and reduced code ambiguity when compared to standard learning from demonstration technique. And we actually show that it especially shows in this mechanism especially prove useful in the few demonstration region where there is a limited budget of demonstration. So first of all, I will present the environment that we are using for our experiments. So this environment is called the fetch bot stacking. It's an environment that has been used a lot in our lab, and that we've been using a lot to experiment with more clever ways to do reinforcement learning by getting motivation from developmental psychology. So in this environment, we have two robots, a learner and a teacher. There are two fetch robots that so they are it's in a simulation, so it's a simulation of the actual real fetch robot. It's a simulation in Mujoko. And the goal of the different goals that there are about cubes. So you have different cubes on the table, and the agents have to learn how to manipulate the cube so that they can do different type of configuration, such that cubes are close to each other or above each other. And then this kind of when combining these different relations, then you can create more complex configuration like pyramids or stack of trees. So in our setup, what we do is that the teacher will provide the demonstration, and then the learner will try to infer the goal of the demonstration, and then it can self-explore what the goal that the teacher wanted him to pursue. So as I said, the goals are based on above and close relation. We encode that into a 9-1-hot vector, a nine-dimensional 1-hot vector, where we can describe if each cube is close to each other or above other blocks. And so this whole goal space is summarized in this 9-dimensional configuration. So now I will present like the overview of our experimental setup, which should help you understand what we're trying to do. So there are two phases in our experimental setup. The first phase is to create the different teachers, because we want to create an optimal teacher, which we call a naive teacher. And then we will try to create a pedagogical teacher, and then which is our contribution basically. And then in the second phase, we will show how we can train the learner using the teacher's demonstration and self-exploration with reinforcement learning. So in the first phase, which is called the teacher pre-training, we have our two different types of teacher that we want to train. So the naive teacher is just an optimal teacher. It will only be trained to master all of the goals. And based on this resulting learn policy, we will use this policy to produce optimal demonstration to have something to compare to. So this would be your usual approach in learning from demonstration, where we only have like a teacher that uses optimal demonstration and that does not try to really change his demonstration to be more efficient in teaching stuff using demonstration. Then to create the pedagogical teacher, what we do is that we take the same process as we did with the naive teacher. So we pre-trained it to master all goals using reinforcement learning, but we will add an additional reward. And this reward is based on whether the teacher can actually infer the goal of its own demonstration. So the idea is that the teacher will use its policy to try to achieve all the goals. And when it actually achieves the goal, it will look at his trajectory, and it will remove the goal, just like if the learner saw the trajectory or demonstration, and it will actually try to infer its own goal. So if it's able to do so, then it will reward itself a little bit more. So the idea is that the resulting policy that is learned will be biased towards learning demonstration that actually disambiguate between the different goals that you want to show. So a little example here with maybe I can have No, okay. So a little example here, if the goal is to put the blue block close to the green block, then this demonstration, this naive demonstration that you see on the top is valid. So basically you did put the blue block close to the green one, but it's impossible to tell if using this demonstration, the intent was to put the blue block close to the green one or to put all the blocks close together. And a more preferable demonstration would be the one that you can see below, where we take the green block and put it close to the green one. And so the idea is that by getting an additional reward when the teacher is able to infer its own goal from its own demonstration, then the pedagogical demonstration will likely be more probable and will be chosen by the teacher. So the policy that is trained for the teacher will eventually lead to only pedagogical demonstration, which is what we show in our work. So that's for the first phase. Then for the second phase, so as I said, the learner is trained using the teacher's demonstration and reinforcement learning. And so, as I said, the teacher will provide a demonstration. Then the learner is going to try to infer the goal of this demonstration and try to follow the resulting goal. I will explain right after how this goal inference is done, because it's a core mechanism in our paper. And so it's interesting to look at it a little bit closer after. For now, just consider that there is a goal inference mechanism that allows you to infer a goal from a trajectory or a demonstration. So in the second phase, you have the literal learner, which is a learner that only tries to infer the goal of the demonstration and then try to master all of the possible goals that you have in the environment. And in the same way, what we wanted to do to add pragmatism to this learner is to kind of add the same mechanism that the teacher has. So the learner will try to better infer its own goals from its own trajectories when it successfully achieves a goal. And so it will get an additional reward for this. And using this, it will the pragmatic learner will prepare itself to better infer the goal of the goals of the demonstration of the teacher. So the idea is to kind of do some rehearsal on your own, trying to infer the goals of your own demonstration to get better when you try to infer the goals of the demonstration of the teacher. So these are the 4 types of agents that we study, and we will show right after what are the types of results that we have. So in here, as you can see, Bayesian goal inference is used in the additional reward system in the teacher. It's used to communicate, to do inference by the learner using the demonstration of the teacher, and it's also used by the pragmatic learner. So it's interesting to talk a little bit more about that. So how does it work? So Bayesian goal inference, the idea is to compute the probability of goals given a demonstration or a trajectory. So the idea is that using Bayes formula, you can actually compute the probability of a goal given a demonstration by inversing just like you have in the Bayes formula. And so basically it's proportional to the probability of a demonstration given the goal. And this is something you can actually compute because the probability of a demonstration given a goal is computable using the policy of the agent. So once you can compute the probability of each goal given a demonstration, then you will sample according to this probability distribution, and so you will most likely sample the most probable goal. And so that's the system that is used to perform goal inference. And basically it has been used in many other work. You can check, for instance, the work of Mark O, which we took inspiration from, that uses this mechanism that works well when the goal space is limited in size. So if you have like 10,000 goals, wouldn't work as well, because Bayesian statistics, basically in high dimension, it's a little bit difficult, but then with a limited goal space, it works well. So now I will show some example of the naive and pedagogical demonstration. So on the left, so it's kind of the same example that I taught a little bit before. Here you have an example of the naive teacher that put the blue close to the red, but it's an ambiguous demonstration. Whereas here, the pedagogical teacher, as you can see, it takes the red and put it close to the blue, so that we don't have any ambiguity over the demonstration. So this is the type of result that we have. It's cool to see that the pedagogical property of the teacher emerges from the additional reward that we implement. So it's not like if we hard-coded the pedagogical teacher to select the right demonstration. It's kind of the teacher on his own training. It actually becomes pedagogical thanks to the additional reward. So to better understand how is the pedagogical teacher less ambiguous, we created some kind of ambiguity score, which is close to the example that I just showed you. So given a starting situation and two goals, we want to see if the teacher provides an ambiguous demonstration for each of the goals. Basically, if you have the same starting situation and two different goals, if a teacher provides the same demonstration for the two goals, then those demonstrations are necessarily ambiguous, because you wouldn't be able to make the difference if you only saw the demonstration. So for instance, for this goal, blue close to red and all of the blocks close together, and then the achieved goals when you have the pedagogical teacher are different, whereas with the naive teacher, they are equal, so you cannot really make a difference. So what we can see in our result is that most of the time, the pedagogical teacher their demonstration results in an ambiguity score that is less high. So here you can see another example of the example that I just gave. So with the naive teacher, for two different goals, it will actually provide the same demonstration. So basically, you cannot really make a difference between the two demonstrations. You can really infer the goal accurately. And with the pedagogical teacher, for the same goals and the same starting situation, the demonstrations are different. And so they are not ambiguous, and it allows a learning agent to better infer the goal. Like this. Okay. So now for the phase 2 experiment, so this was all about the pedagogical teacher. Now we move on to the learner trying to learn all the tasks and using the demonstration of the teacher. What we can see in our result is that so the pedagogical plus pragmatic combination, so pedagogical teacher and pragmatic learner combination results in more efficiency. So the end result is better, and also it learns faster. And it especially shows when you have less and less demonstrations. So for instance, here with 100 demonstrations per goal, what you can see is that actually using a naive teacher and a literal learner, you cannot really solve the task. Whereas with the pedagogical teacher and the pragmatic learner, you can actually solve the task. So we can see an example here. So with the pragmatic learner and the pedagogical teacher, it learns to do stack of threes. And with literal learner and naive teacher, it tries to do the stack of three, but it actually actually fails, and so that's why it's important to add pragmatism and pedagogy. So this is it for this paper. So if you want to learn a bit more about this paper, we have a full description of our approach and of our experiments in our paper. Now we will do a quick note on the work that we are doing at the moment. What we are trying to do at the moment is to kind of move on to multimodal Bayesian goal inference, and using demonstration and also language. So the idea here is that just like demonstration, there are many true instructions, but that can be ambiguous. So in this different setup, what we do is that we still have the fetch robot trying to stack and move different cubes. But now we have cubes that have properties, and these properties, you can use them to refer to the different blocks. So the blocks, they have a color, so they can be blue or red. And also they have a texture, kind of like drawings on them, and they can be striped or they can be plain. And if you make the assumption that you can use only one feature to talk about the goal you are trying to communicate using features, then there will be some referential problems. So for instance, here, if we take the goal, if we take this goal where we want to have those two cubes together, and this different goal where we want to put those two cubes next to each other, then the instruction put the blue cube next to the red cube is ambiguous. So basically, in the same way, when you're using instruction to communicate a goal as a teacher, you can select different type of instruction that might be a little bit more ambiguous or not. And so we did actually a workshop paper at NeurIPS on this, and we had some first results on this. And now we are trying to see if we can combine language and demonstration on the same setup, and to see whether it's better to start with demonstration and then give some instruction, or to do the opposite, or is there an optimal scheduling to give teaching signals such that the learner learns faster. And so for that, we actually want to compare ourselves to real work in cognitive science, where they actually showed that the demonstration might be more useful at the beginning of training, and instruction are more useful at the end of training. And so we're trying to see if in our setup, this type of result also holds. And so that's the idea of the work I'm doing now. And the long-term idea for this type of work is to have whenever we will have robots in our daily life with which we interact with, it will be useful for them to have learning systems that can be sensitive to this type of pedagogy and stuff, because it will be more efficient. And so that's why we are working on this. So I think that's it for my talk. If you want to contact me by email, I put my email here. And for the different papers, so on demonstration, you can go on this paper on archive. And for instruction, there is also the paper that is mentioned here. And thank you very much for listening. And I'm open to questions now. Or maybe I'll leave my slide here, maybe. Would be useful for a question. Yes, so.
I have a bit
I can't really hear you.
I think her connection is kind of becoming unstable.
Okay. Thanks for coming. Who's talking actually? Silvia.
Guys, can you still hear like that echo thing happening in the?
Yeah, I can hear it too. I was just waiting to see if Silvia has a fix. I think Silvia has become a robot. Yeah.
Can you hear me? Can you hear me? So I have a question.
Yeah, a little bit better now.
I think your internet is still causing problems.
Yeah.
Yeah.
Hey, I do. I have a question. Hi, Hugo.
Hello.
Wait, I'll wait for Sylvia's echo to slow down. I think it's a great background voice. Okay, so my question was a great presentation. Love to see your new work as well.
Maybe someone can mute her, no? But she's already mute, I think.
I think it's okay. Okay, perfect. It was great to see your current work. It's, question as well, but the internet is... I think what she said previously is not coming.
Yeah.
I will ask. Okay. Is it good? Perfect. Okay, I'll go into my question. I was wondering, like, can your work be reversed as well to do like explainable AI? So that because you said that the agent is figure out what the goals are, and so if you were to ask, so why did you do this, and would they be able to, like, would the agent be able to explain their own actions based on that work?
Okay. So you would want the teacher to kind of know why he did this demonstration, basically. I think something that we are looking at the moment, we'll have like an internship on this, is related to what you were talking about. So the idea is that what we wanted to have is that, so in this setup, for now, the teacher is not adapting to what the learner does during training. And so it would be better to select the best demonstration for this learner. And so what we wanted to do is for the teacher to have a model of the policy of the learner, and trying to see if the teacher can select the demonstration that has the maximum chance of being successfully inferred by the learner. So for this would be kind of like explainability, because you would know why you selected this demonstration, because it's the most efficient for this particular learner. So that's something we're trying to work on, and we'll see if it works or not. But I think it's one of the ways to do it is to do some kind of theory of mind and trying to kind of understand what are the preference of the other agent, so that you can select what is most suited for this particular agent.
That's great. You're doing that kind of like personalization then.
Yes.
We're doing it in totally different areas, but that's perfect.
Yeah.
And also, so do you think that it will be able to generalize to other tasks as well?
So for now, I think our setup is would definitely work on any type of setup where you have multiple goals and where there exists some type of ambiguity with the different goals. So basically, if you have I don't know which type of task, I don't have any type of task that comes into mind, but basically if you have if you want to demonstrate something and you can be ambiguous, which happens a lot in real life, then any type of multi-goal environment would benefit from this. And basically the idea is to say that you don't really have to really change your setup to implement this, because you only have to add an additional reward to your agents. So basically, I think any type of multi-goal environment would either benefit from this or it wouldn't change the performance.
That's great. What came to my mind actually is I don't know if you've seen the peanut butter and jelly sandwich with the two children and the parent, the father. Oh, it's really related to what you're working on. The father tries to do like a peanut butter and jelly based on the instructions the children are giving to him. And like put the peanut butter, and then he puts it with the other side of the knife because it's ambiguous, like which side. And so you can maybe try that with a robot. That would be super cool.
yeah, definitely. I think I don't have any example that come to mind, but this type of ambiguity happens like in most of the multi-goal environment, because basically if you're working with a learner that doesn't know anything about the world and stuff like this, like a robot, then it can infer really weird stuff and do counterintuitive stuff. And this and I think pedagogy helps to kind of battle against this type of counterintuitive behavior that the robots might have.
Thank you so much. I already asked so many questions, so it was great to see you. And I'll just like go now. See you. Bye.
Bye. So is Sylvia back? I don't think so.
I think she's back again in her old form.
No.
Because I still see like some lag in the video and.
Really? Okay. She's still there?
I think she's there, but.
Yeah.
Okay.
Okay.
Okay, because like your question did not get through because of connection issues. If you want to ask it back, if it works better now.
No.
Well, I had a question.
Okay.
So, have you like tried like using some kind of like language or grounding in your research to help with like trying to identify what's the most relevant way to do a task? Like I've seen people do research, but that was more like natural language for robot learning, and they've used like semantics and like structure.
Yeah. So I see what you mean. So the idea in our work, with natural language and instructions, we are actually not interested in the grounding problem. We are more interested in so let's say you already have a method that can from natural language kind of isolate different types of goals, and then what we want to do is to make it so that the natural language, when you receive it, you can map it to the right goals and not make mistakes to the type of goal you're trying to map. But the actual grounding, we are not yet interested in this, because I think it's a little bit of a different problem. In our work, we are really only interested in goal ambiguity, and we're trying to work on this. But then the language grounding and is kind of a different problem, because you want to map a very a very messy space with all the natural language to different types of high-level goals. And in our work, we actually assume that we already have the high-level goals. So I think creating this type of goal space from a natural language is something very interesting, and there are many works on this. But in our type of work, it's not really the thing we're interested. We are kind of building the block that will go after the language grounding.
Got it. Thank you.
Thanks.
Maybe I have a quick question. Like,
Yeah.
For these tasks, do you have also like certain preferences that you take into account while doing the task? For example, if you're doing like a grasping task and you change the location, and depending on the location, the grasp might change, like feasibility of the grasp and stuff like that. Can you also do that using this method, or this is something?
Yeah, it's actually a great question. We don't have this type of grasping, this type of way to grasp problem on a particular cube, but we do have a type of problem. So, for instance, if we didn't do any experiment on 4 or 5 cubes, it's because we kind of have this problem. So, because you learn the policy with reinforcement learning based on rewards at a particular time step, and the reinforcement learning is trying to maximize over an episode the number of rewards, of accumulated rewards, then the agent really tries to get to the configuration like the stack of 3, for instance. He really tries to get this configuration quickly. And so one way to do it is when you grasp the cubes. For instance, if you want to do a stack of 3 with 3 cubes that are next to each other, the agent will grab one, put it on the next one, then grab the stack of 2 and put it on the stack of 3. And actually, if you want to do a stack of 4, this is a problem because the grasping hand, when you want to grab the stack of 3, it's too short. So you cannot actually grab the stack of 3. And that's why the reinforcement learning usually fails. So I think it's really interesting to see if we can solve this type of problem by having a teacher that actually gives the right demonstration and that shows that no, to create stack of 4, you have to be patient and you have to take one, put it on the next, then do 2 stack of 2s, for instance, and then put the stack of 2 over the stack over the other stack of 2. And so I think this type of the learning from demonstration really can be leveraged here, because with reinforcement learning on its own, there are some tricks where you can actually solve this problem. I have a colleague that work on this, but I think it's more suited to have a few demonstrations that show that no, you don't have to really, you have like a short grasping hand, so you have to do a different method, even though you feel like you are missing on potential reward because you're not going that fast. But so this is another type of ambiguity. I think it's a little bit more important ambiguity, because if you want to do it this way, you actually can't do it. So it's even more important. But I think this type of approach is really suited to this type of problem as well.
Mm-hmm. Thanks for the answer. Maybe like just a quick understanding question, like a last one. Like how are the plans are generated in the first place? Did you have like an initial seed from where you, like the robot, the teacher basically generates these plans, or it's like a one demonstration, or is it like
the plans, you mean the demonstration?
Yeah.
Okay. So what we actually do is that so for the teacher, what we do is that once the teacher is trained and can master all the tasks, the teacher will sample a random goal, and then it will plug this goal in its goal condition policy, and it will do a rollout of this policy, achieving the goal, and this is the demonstration, basically.
I see. Thanks.
I also have a question.
Yeah.
The question then would be if it's maybe a good approach to such a problem to like interpret the corrections, because we only have really few examples in our scenario. Like we want to learn a co-constructed goal within like 80 demonstrations.
Yeah.
And we don't have the time to really well, not only the time, but we also don't have the participants to make a pre-trained model on trajectory attributes, for example. And that sounded very promising, that this intention derivation that you presented.
Yes. So I do think that the ideas of pedagogy and pragmatism are applicable to your problem. Basically, those ideas, we wanted to apply them on demonstration because that's something that we wanted to work on. But more generally, I think these ideas do apply to any type of teaching scenarios. So the type of teaching scenarios you are referring to here are feedback that are given during the learner's process. And this type of feedback can be natural language, for instance. So there might be lots of referential ambiguity or this type of ambiguities that emerge from this feedback. And the way you give that feedback is very important. So some instruction might be more ambiguous than others. And so I do think that here you have to consider, you have to kind of understand what is the nature of your teaching scenarios. If it's natural language with feedback, then maybe you can think of how can I do a pragmatic inference over this type of teaching, over this type of teaching scenarios. So I think the way we visualize the problem is to say, what would you infer from this feedback, for instance? So put yourself in the shoes of the robots, basically, and see if there is a way to for the teacher to provide more accurate teaching scenarios. So I think for the human is to say that if I was the robot, would I be able to understand this feedback unambiguously? And so this can be applied with Bayesian goal inference, for instance. Or if you're only working with humans, basically you have to tell the humans, do not like give feedback randomly, or like try to put yourself in the learner's shoes. And then in a more automatic way, maybe you can modify the learner's policy or the way the learner actually trains, so that it tries to make more accurate inferences about the teacher intent. So for that, maybe I would look into my work, but you can also look into the work of Mark O, who does a lot of good work on this, and also Yoan Gueon, so Gweon. She does a lot of very good cognitive science and developmental psychology work on experiments with real humans and children, and I think you can get lots of really cool ideas from their work. That's what I did, and it actually works well because in their field they actually test stuff with actual human, and they have lots of very big experiments that lead to a good conclusion that you can apply on your robotic setup, and hopefully it works or improve what you did before.
Thank you very much for
Thanks
the
so much.
talk and the answer.
Thank you.
Do you guys have more questions for Hugo?
Yeah, I think that was it.
Yeah, I think that's it.
can-
Perfect.
Thank you, Hugo, for joining for the talk once again, and we can wrap up quickly.
Yes. Can you see my screen?
Yes.
Yeah.
Awesome. So thanks for joining, and thanks, Hugo, for the wonderful talk. I'm very glad you got to present, and we had a nice discussion as well. And so this is our last session before holidays, so hope you all have a good vacation. But and right after we come back in January on the 11th, we have Dr. Danfei Zhu from Georgia Tech coming and joining us. So he's a professor there, and he works on he's going to talk about like bridging reasoning and acting for everyday autonomy. So hope you all get to join us, and see you all in January. Thanks. Bye.
Thank you very much. Bye-bye.
Bye.